Okay, everyone, we're in for an exciting new week. We've got a new topic now called analysis of variance. Analysis of variance is usually just pronounced by this abbreviation ANOVA. So you'll hear me say ANOVA a lot, and you'll see it written in all caps, like it is right there. So in introducing ANOVA, or analysis of variance, we first need to know when to use it and why to use it. And to kind of introduce that idea, I'm going to show you a sample from a published abstract of a pretty simple ANOVA. So the when and why are the two main things in this video. I'm also going to introduce some important vocabulary throughout. So after you watch it once, you might want to go back through and jot down those words, make sure you understand those. Some of them are words I'd like you to know that aren't necessarily in the textbook either. So I'll make sure to highlight those definitions and write them down. So anyway, when to use ANOVA. All right, so there are two situations that we're going to study. The first one is when you are testing more than two groups on a single independent variable. So when I use IV there, I'm going to use that to represent independent variable. In that situation, we call it a one-factor or one-way ANOVA. So if you hear someone say one-way ANOVA, they've got an experiment with more than two groups in a single independent variable. So, quick example, we did the study with the stairway versus the elevator. That was the independent variable, and there were two groups, stairs and elevator. Now, you can imagine we could add a third group where someone like floats up in a balloon or something like that. That would call for a one-way ANOVA. The other situation is you might still have only two groups for your independent variables, but if there's more than one independent variable. Now, in the language of ANOVA, a lot of times the independent variable is also called a factor, and it's called a factorial design if you have more than one. And that's all I'm going to say about that today. I'll have another session that introduces factorial ANOVA, but it gets a lot more complex, so we're going to focus on the first of these two things right now. So, here's that abstract I was telling you about. It was about a study on the Mozart effect. The Mozart effect was this thing that was purported to show that if people listen to Mozart piano music within a certain period, they actually do better on like spatial cognition things. So think about maybe some games you played as a kid where you had to remember the location of several things. And those types of activities, people were supposed to get better. But that turned out probably to be something that somebody kind of fudged in order to sell CDs. And so a lot of people try to replicate the study, and this abstract is an example of one of those. So I'm going to pause for a second, let you read the abstract, and I want you to pick out the independent and dependent variables. Okay, so here's what I came up with. I named the independent variable type of music. There's a lot of different ways to say that. You could say classical jazz or silence or something like that. The dependent variable here, the outcome, is spatial reasoning. So here we've got a situation with one independent variable and one dependent variable. Now, the reason we choose ANOVA has to do with the nature of the independent variable. In this case, I want you to see how many levels we have. When I'm talking about levels, I'm talking about how much does the independent variable actually vary. In this case, we have classical, jazz, and silence. So, here's the thing. That's a situation where you use ANOVA because you have more than two groups. If you only have two groups, you would just do that with a t-test. And, you know, you could actually analyze this study using a series of t-tests. But I want you to see that t-test multiply really fast here. So if I have 3 levels in my study, how many t-tests can I do? You might pause for a second and try to see how many ways you can pair those up. All right. I came up with 3 t-tests. I can compare the classical group to the jazz group, the classical group to the silence group, and the jazz to the silence group. And in the language of ANOVA, we would call each of those pairwise comparisons. And the term pairwise there just means that you're only comparing 2 conditions at any one time. So if I say, are any of the groups different, someone might say like classical and jazz are different. Well, that's a pairwise comparison because even though there's only 3 groups, you select 2 to compare at any one time. So in this case, we have 3 pairwise comparisons. But what I want to show you is that the addition of levels can actually create a situation where you have mind-boggling amounts of t-tests. So think about this. Are there more than 2 types of music? I believe there are. You could actually add another one. I tried to add something I thought none of you would think of, which is polka. If the experiment looked like that, here you would be saying that classical music is somehow different than jazz, silence, or polka, and your experiment would be looking at that. I want you to hit pause and see how many t-tests would be involved in that. Remember, there were 3 t-tests when there were 3 levels. Okay, there we go. In this case, there are actually 6 t-tests. As you can see, classical is compared to the 3 other ones. Jazz here is compared to classical already, so I only have to add silence and polka. Silence has been compared, appeared to classical, appeared to jazz, so I only had to add polka. So with 3 groups, we had 3 t-tests, 4 groups, that multiplies all the way up to 6. In fact, there's this thing right here, this formula, which is not in the book, so please pause and take a note at the end of this page or come back and review it. This tells you how many possible pairwise comparisons you have. So that capital C in this formula stands for comparisons and P stands for pairwise. In order to do this, you have to know that we use the letter K to represent the number of groups. So up here, I have a K of 4. There are 4 different levels or 4 conditions. Notice that what I'm doing here is multiplying it by degrees of freedom. So 4 groups gives us 3 degrees of freedom. All that's saying is that if you focus on classical, there are 3 other things that it can be compared to. And then you divide that by 2. And the reason we divide that number by 2 is because we don't have to compare classical versus jazz and jazz versus classical. So if we multiply 4 times 3, we get 12, but then we divide that by 2 because we don't have to do both directions of the comparison. All right, so when I work through that, I see that I have 6. So that's a useful formula for understanding how quickly t-tests will multiply. And as you can see, it multiplies pretty fast by a factor of degrees of freedom. Okay, so as I've been saying so far, ANOVA helps when you have a lot of t-tests. But then there's still the question of why do we use it? I mean, if you're using a program like SPSS, you can do 6 t-tests just like that. The reason that we do this is not because t-tests are slow. They're not slow at all on SPSS, but what happens is that every time you reject a null hypothesis, that alpha 0.05, your chance of error gets a little bit bigger. ANOVA reduces that, okay? I'm going to walk you through how this happens. So remember that in a pairwise comparison, we'd only be comparing 2 of the groups. So let's say we're comparing classical and jazz. That's a pairwise comparison. If we did that with the t-test and alpha of 0.05, our alpha would be perfectly fine for that specific test. But remember, in the experiment, that happens over and over again. And if you reject the null hypothesis multiple times in pairwise comparisons, that alpha starts to add up. Now we want alpha to be 0.05 because that means we have a 0.05 chance of type 1 error. And in a t-test, that was fine because pairwise and experiment-wise were equal. But in ANOVA, where you have multiple pairwise comparisons, the experiment-wise gets big really fast. So let me illustrate this process for you. In the abstract, there were 3 possible pairwise comparisons, as I've listed there. If we did each of those with the t-test, I don't know why that 0.05 scooted over, we would have a 5% chance of type 1 error for each of those. But experiment-wise, that would shoot up to 0.15. Not exactly, but that's an estimate. If you're interested, there's a formula that you can look at down there that tells you. But had we rejected all of those, we'd have a much greater chance of type 1 error, 14% and then some, when really we're only willing to go up to 0.05. So what we have to do is find a way to do a test to keep this from going up. Now, that is when we do ANOVA and why. I'm going to tell you how it works, and we're going to walk through later, but I thought I had enough time here just to say that ANOVA is practically the same thing as a t-test. Notice on this screen, if you want to take a pause here, you'll notice that it's the same 4 steps as a t-test, so we're not learning new logic. In 2 sample t-tests, if you look at this, you see that what we're looking at is a ratio of the difference between 2 groups over how much you would expect those groups to differ if the null hypothesis is true. Now, an f-test actually works with variance. MS between is actually the variance among group means. So rather than just saying the difference between like before and after or stairs and elevators, because we have 3, we're going to calculate variance. And instead of having standard error, which is a type of standard deviation, we're going to have variance. Okay. So basically the only difference here is we're moving from measures of standard deviations, or standard error, to measures of variance. The difference between groups and the variance between groups make up the numerators. The expected difference and the expected difference makes up the denominator. So they are literally the same concept. And in fact, if you did an analysis of variance with only 2 groups, you could take the square root of f and you'd come up with the same thing as a t. So the only difference really is that the f-test, which is used in the analysis of variance, allows you to compare more than 2 groups, which you just can't do with a t-test. And that has to do with the fact that with 2 groups, you know that one group minus the other should be 0 when the null hypothesis is true. If you have 3 groups, you don't know that one minus the other would be 0. In fact, it's impossible to determine. But you do know that the amount of variance among 3 group means should be greater than the regular amount of variance if your research is correct, your alternative hypothesis is correct. Okay. So here's the final screen. That's the recap. That's a lot of stuff. You might want to go back and look through those things. And when I say pause in the video, it might be good to pause a few times to make sure you're able to anticipate the answers and understand how to differentiate between an independent variable and dependent variable, know the difference between a level of an independent variable and the independent variable itself, and make sure you know how the increase in pairwise comparisons leads to an increase in type 1 error. Next video, we'll probably look a little bit more at how this whole thing works, and then we'll do some calculations in the third video.